All right, let's get started. First, I wish to thank the program committee of the LEX conference for inviting me to give this tutorial, which is dedicated to the subject of explainable AI, and in particular to a theory of explainable AI that's based on symbolic logic, and that actually did contribute some elements to symbolic logic, as we will see later. So this theory is concerned with the following picture. As we know, a lot of what's going on in AI is based on classifiers. They can take different forms: Bayesian networks, neural networks, random forests. These are boxes that are numeric in nature. They're learned from data, and they effectively map what we call instances to decisions or to classes. For example, a box may decide whether a loan application should be approved or declined. And since these boxes are learned from data, and also given their intricate and numeric nature, they're not as transparent. And people want to know what is it that they're doing, and why are they making the decisions that they're making? So there is a whole set of questions that are of interest that fall under the umbrella of explainable AI. As we mentioned, why was an application declined? Is there a minimal way to change this application so that we can get it to be approved? How robust is the decision? Did the decision depend on some protected features and therefore biased, and so on? So the main insight that this theory is based on is that even though these boxes are numeric in nature and learned from data, the decisions they make are finite. So it's a discrete set. And the input to these classifiers is often also discrete. And in some cases, when it's continuous, can be easily discretized. So because of this, we can sometimes and often compile the input-output behavior of these classifiers into a symbolic representation. And if we're able to do that, then we can use logical reasoning and logical analysis in order to answer explainable AI queries. And that's exactly what we will be doing here. Now, to internalize this picture of compiling input-output behavior into a symbolic representation, let's look at a concrete example. This is one of the simplest numeric classifiers you can see around. It's called naive Bayes classifier. We have three features in this case, and we have a class variable. There is a class distribution. These numbers represent false positive and false negative rates of the different features. And typically, one gets an instance, which is a patient, and that's a setting of these variables. Compute probability on the class variable, which is pregnancy, checks against the threshold, and then renders a decision yes or no. So we're doing probabilistic reasoning here to classify or to make a decision. But if you realize the input, that is, the instances are discrete and the decisions are discrete. So this is just a fancy way of specifying a discrete function. And we can obtain that discrete function in symbolic form. In fact, in this case, this classifier can be represented using this decision graph. So if you have this particular instance, you can just follow the paths in the traditional way, and the classification here is that this instance is negative, or this patient is not pregnant. Now, in fact, in this case, we have only 8 instances, and both boxes, the numeric and the symbolic, will make the exact same decision. And this is guaranteed because this symbolic representation was actually obtained using a compilation procedure or algorithm that we will mention later. Now, when you have a picture like this, a number of questions come up. One, what other classifiers can we compile into symbolic form, and how can we do that? The other element is, what is the symbolic form? Here I'm showing a decision graph, but that's just for illustrations. Decision graphs are nice to visualize symbolic representations in this case, but it doesn't have to. And then the third and beefy and main question of interest here is, what can we do with the symbolic representation? How can we process them so that we can answer the kind of questions that we talked about? And that's going to be the bulk of the tutorial. Actually, we look at all 3 elements but the bulk of the tutorial will be on the third one. And here we'll see some interesting things because the theory, as I said, will be based on symbolic logic, but some elements of it were actually introduced. There is some elements of it that pertain to symbolic logic were introduced because of the needs of symbolic of explainable AI. So this quest of symbolic AI actually did make some contributions to symbolic logic, and some profound ones, as we will see later. So I just want to make one remark before we move on, that one may think that this is the end result, that because there's this perception that decision graphs or symbolic representations are interpretable. That's not the case. In fact, even the small decision diagram, will kind of come back to it later, and you'll see that it will surprise us in certain ways. And these things can be very large, so they cannot be visualized by humans or interpreted. In fact, for some of the case studies we looked at, including this one, where we compiled classifiers in the domain of education. These were the classes, and we're trying to assess skill level for students based on answers they give to questions. Here's another one from troubleshooting. I think this network comes from Microsoft Research. Here's another example from Stanford Medical Informatics for diagnosing breast cancer. And for these and others, you can see that the decision graphs that we compiled, for example, ranged from hundreds to a few millions. So clearly, you're not going to visualize this or even these. So I just wanted to emphasize this before we move on. Okay, so now, what kind of classifiers can we compile into the symbolic form, and how? It's a subject that we're going to talk about at the very end of the tutorial. But before I start, I just want to make a few remarks, a couple of slides, so that, again, we internalize some important messages here. If you look at the three types of classifiers that I mentioned, Bayesian networks, neural networks, and decision trees and random forests, and people have compiled definitely these and those and some restricted types of neural networks into symbolic representations. You'll find that conceptually, the simplest are these. And the reason is, as you'll see later, they're almost symbolic. The most complex are Bayesian networks. And the reason is, in neural networks, the reasoning or the classification process is relatively straightforward because neural networks are feed forward. So you go through a forward pass in the network and you reach your decisions. In Bayesian networks, it's a lot more complex. There is some complex reasoning that's taking place there that is needed to decide what class an instance belongs to. So conceptually, they end up being more involved. Now, I'm showing only references for this. For these, there's significantly more references. There is a paper that goes with this tutorial. It appears in the Lex proceedings. It's also available on the archive. You'll see citations for other compilation methods. And let me mention also, there's a lot of work in the community that is concerned with, for example, verification of neural networks, and other tools are used for that purpose as well, beyond what I'll be talking about here. The other thing I want to mention is, fine, this example that I showed you here, it was obvious that the input is discrete, the output is discrete, and then you can imagine that we will be able to compile this into a symbolic representation. But what about something like this, where we have, let's say, a decision tree, and we have features that are numeric in nature? So in this case, we have actually an infinite number of instances. Take this instance, for example. We have two features only in this case, and age is 30 and BMI is 27. Here's another instance in this case. It's different, but actually both of these will be classified the same way into a yes decision. And this is not arbitrary. What happened here is, from the point of view of this decision tree, and if you examine it carefully, you'll find that all it cares is whether age is in one of these three intervals and whether BMI is in one of these four intervals. In a sense, even though we have an infinite number of instances, we do have a finite number of equivalent classes of these instances. So both of these instances belong to the same equivalence class, where age belongs to this interval and BMI belongs to that particular interval. As such, we can treat these variables as actually discrete and give them these labels that correspond to the intervals, and we can view this classifier as the symbolic one, all right? And the nice thing here is this chopping of a continuous variable into a number of discrete values is done by the learning algorithm itself. All right, so yes, so both of these instances would be abstracted into the symbolic instance and classified this way using the symbolic representation. So it's this that we will operate on. All right, so now let's get to the second element, which is what symbolic representation do we compile into, and the representation that will end up being the subject of our logical analysis or logical reasoning. Now, in our earlier work on the subject, the compilation algorithms we developed, or the work we did on explainable AI, was strongly tied to representing these classifiers using circuits, Boolean circuits. That was the choice for the symbolic representation, and in particular, what's known as tractable circuits, like decision graphs. And now you say decision graphs, are they circuits? They are indeed when you account for notation. So if you look at this decision node here, it says if X is true, go this way. If X is false, go that way. We can represent it by this circuit fragment here. And if we repeat the same process for alpha and beta and do it recursively, we get this circuit. And it's not just any circuit, it's what's known as an NNF circuit, negation normal form circuit, in the sense that the leaves are either variables or their negations, known as literals or constants, and then we only have ands and ors. And in fact, this is not just an NNF circuit, it's a tractable one. It does satisfy some properties that allows us to do certain processing on it efficiently. So it's both decomposable, satisfy the decision and ordering property, and so on. My point. This is just an example of a tractable circuit, which is the binary decision diagram or the ordered binary decision diagram. And there's a whole theory of tractable circuit that is studied under the banner of knowledge compilation in AI. Over the last 20 years, and mostly starting with this paper, this theory have studied dozens of tractable circuit representations, based on negation normal form and different properties and what circuit types they lead to. And in fact, these tractable circuits can be even thought of as a model of computation, because if you look at complexity classes like these, for example, you'll find that the prototypical problems for these complexity classes are all questions on Boolean formulas, or you can think of circuits. And for each one of these problems, we do know of circuit types or circuit properties that will allow us to answer these questions in polynomial time in the circuit size. So again, in earlier work or earlier presentations on the subject, I would spend about 20, 25 minutes on this part. Now I'm not. I'm just going to have this slide. And as you'll see next, we have recently abstracted the symbolic representation into a form that is sufficient for what we want to do, and we decoupled from this theory of tractable circuits, which simplify things quite a bit, as you will see. But if you're interested in hearing more about the subject, I did give a 2-hour tutorial on this at the Simons Institute, I think about a couple of years ago. It's on YouTube, you can find it, and I actually teach a whole course, graduate course on the subject at UCLA, that is available online as well. Here's our YouTube channel link, and you can find it there. And if you like to read, there's a couple of papers. There's a POTS tutorial from a couple of years ago, and the most recent is this book chapter from a book on Eurosymbolic AI. These circuits also play a role in Eurosymbolic AI, where people use them they couple them with neural networks to regularize and to impose constraints and so on. So they're a thing in that area now. Again, this book chapter is available on the archive. All right, so let me tell you now about the particular representation that we'll be using. As of a year or 2 years ago, we started using or representing classifiers using class formulas, which means the obvious. as you will see now. Let's look at this example again. We have three features in this case, and they're all binary variables. Let's adopt this notation. A binary variable x has two values or two literals, positive and negative, or true and false. And this is a binary classifier, which means it has two classes, pregnant, not pregnant, yes, no. So I will need two class formulas, one formula for each class. And the purpose of each formula is to characterize the instances in each class. So this formula here characterizes the positive instances. Out of the 8 instances or truth assignments for these three variables, 5 of them satisfy this formula, and these happen to be the positive instances according to this classifier. And this is the class formula for the negative instances, which in this case is just the complement of that. Now, in this example, it happened that the features are binary, and also the classifier is binary, so two classes, but we would not make either restriction. So in general, we will allow discrete features and multi-classes, such as is happening in this classifier. This is a decision graph. There are three variables, x, y, z, and they are all multi-valued in this case. In fact, each one of them has three values. These are the three values for this guy, and these are the three values of that guy, and so on. And we also have three classes in this case, C1, C2, C3, and here's an example instance. The feature X has this value, feature Y has that value, and feature Z has this value, and this instance happens to be in class 3. So in this case, we will need three class formulas, one for each class. And here's how they look. Now, as you'll see, we're starting to use a non-standard notation. So if you look at this particular notation here, it basically says that the variable x took the value 1 or 2. So it's like a disjunction. Now, in just a little bit, we'll define the syntax of this clearly, because we'll be using what we're going to call discrete logic as opposed to Boolean logic when representing these formulas and when we're formulating our theory of explainability. And this is actually an interesting choice, as you will see. Because earlier works were mostly based on Boolean logic, and we'll see that that has issues. So this here says that the variable x took this particular value. Again, this is a disjunction. It's saying the variable y took the values 2 or 3, and so on. Now, this classifier has 27 instances, and 20 of them satisfy this formula or are characterized by this formula, 3 of them by this and 4 by that. So a classifier is effectively a partition of the instances where each element of the partition corresponds to a class, and the formulas are basically describing the elements of this partition. So in general, they're a set of mutually exclusive and exhaustive formulas, and they're in one-to-one correspondence with the classes or the decisions. And typically, they are represented as tractable circuits, but we're going to come back to this later towards the end. And in particular, just make a hint about also some recent results that tell us what kind of tractable circuits are needed to facilitate the computation of explainability queries. So it turns out there's a nice simple property that actually in a way missed in earlier work on tractable circuits, and that emerged in the recent work on explainable AI. We'll go over this later. Okay. I just want to emphasize a little bit this distinction between binary versus discrete variables, because as I said, the theory that I'm going to be describing started initially using Boolean logic. But most classifiers have discrete variables, and the traditional way of dealing with that is to binarize these variables. So if you have a variable like color, which has 3 values, then we end up introducing 3 Boolean variables. Color is red, color is blue, color is green. Of course, you have to add some constraints to make sure that exactly one and only one of them is true at a time. There are issues with this, and in our recent work over the last 2 years, as opposed to the last 5 years, we started actually doing what we call working with native discrete. We do not discretize, but work directly with as I'll show you next, discrete logic. And the reasons are both computational. Sometimes you can have many thousands of values for a discrete variable, and you don't want to create that many Boolean variables. This happens, for example, in random forests, because each decision tree end up chopping the continuous variables in different ways. And when you start combining the different trees, the number of values grows. But there are also semantical issues, as we will discuss later. In fact, when you take what was developed for explainable AI in the initial phases, based on this theory, and the formulation that was done using Boolean logic, and apply it to situations with discrete variables, you end up missing. And this is an observation that was made a number of times, and we just provided the most comprehensive proposal for dealing with this, which is something we're going to go over later in the tutorial. This is a very exciting and recent developments, as we will see. So as I said, we will be working with native discrete, and what this means is we will be using discrete logic as opposed to Boolean logic. So what's going on with this logic? The main difference with Boolean logic is the variables here are assumed to have a finite number of values, not necessarily true and false. A variable can have up to n, and we call them states. And the key thing here also in the syntax, in Boolean logic, you have x and not x. So x is true and x is false. Now we have the notion of a literal, which is a set of states. So if this variable has those states, then a literal is a subset of them. It cannot be empty, and it's a strict subset. So here's an example literal for the variable x, which effectively says that I'm telling you that the variable x takes the value 1, 3, or 4. And we use this often in this tutorial as a notation. So when I write this, this represents this set, and it's a literal, and it's basically saying that the variable x takes one of these 3 values. A special case is the notion of a simple literal, and this term is going to be important later. And this is a literal that has exactly one state. So in this case, I know definitely what the value of the variable is. I know that the value is this one. So in Boolean logic, we have only 2 states and only simple literals. So literals can only be, according to this definition, it can only be this or that, which effectively saying that the variable x is true, and this says the variable x is false. For simplicity, we'll just notate them that way. Other than that, you construct formulas in the usual way, either using constant true, false literals, or you can negate a formula, you can conjoin 2 formulas, you can disjoin 2 formulas. And we will say that the formula is simple if it only contains simple literals. And then you can define other notions, like a term is a conjunction of literals, a clause is a disjunction of literals, CNF, DNF, classical ways. The notion of negation normal form formulas ends up being very important in this theory. It's a formula that has no negations. So you can only have literals, and you can compose them using ands and ors. You don't need negation. You cannot use the negation in this particular form, and as you'll see, it will play an influential role in this theory. Let me just mention something important. If you take this discrete logic and focus on simple formulas, that restriction will end up being important, because we're going to see 2 versions of the theory. The one that has been maturing for almost 5 years. And it's based on simple formulas, all right? And there were interest in going beyond that. And as I said, as a few months ago, we presented a comprehensive proposal that extends this theory and ends up using formulas that are not simple. So we'll see this distinction coming up. But since we're on it, and now we have a clear syntax, we will say that a classifier with these classes is simply a set of mutually exclusive and exhaustive formulas that we will call class formulas. And now an instance formally is defined as a conjunction of simple literals, one for each variable. So an instance simply fixes the state of every variable, And we will say that an instance I is in a particular class if it implies the corresponding class formula. Now, I didn't define the semantics of this logic here. In the paper that's associated with the tutorial, that is defined, but it is basically a simple extension of the semantics of Boolean logic. Now, you'll hear me talk about features. Those are just the discrete variables. When I say characteristic, it means a simple literal that is a particular state of a particular variable. And in that sense, an instance can be viewed as a set of characteristics, one characteristic for each feature. All right, so now we can get started with the beef, which is what do we do with these representations? Meaning, assuming that you took your classifier and somehow managed to compile it into a set of class formulas, one class formula for each class, what can we do? And what we'll do is answer a number of questions in Explainable AI. We're going to start simple and then grow it. And in fact, we're going to start with the first question that we tackled, which effectively started this area of what people call formal explainable AI. Of course, explainable AI had a longer history, and just before 2018, there were approximate approaches that were very popular and still very popular. But this refers to a theory that's exact, as we will see. There are no compromises here. The notion that we introduced in this paper, we called it then PI explanations. Later, we called it sufficient reasons, and you'll see why did we make the switch in names. But this is a very simple and influential, turned out to be a very influential notion. So if you have a classifier, it's a box, you pass it an instance. Let's say you have 100 features, and therefore the instance is a value for each of the features, and a decision comes out. A sufficient reason for the decision is a minimal subset of the input, of the characteristics that you passed as an input, a minimal subset that guarantees the decision. So if you had 100 characteristics as the input to the classifier, and I can come back with 7 of them and tell you these 7 are sufficient, meaning you can change the other 93 in any way you want, and the decision will not change. And moreover, no subset of the 7 will have that property. That's basically what a sufficient reason. In words, again, minimal set of instance characteristics that can trigger the decision. Now, let's take a couple of examples so that we see this concretely. And let's start with a simple example because we already have it. In this case, we have a patient, Susan, who tested positive for scanning blood and urine. So we can view it as this particular instance, 3 literals, 3 simple literals. This says that scanning is positive, blood is positive, urine is positive. Okay, now if you look at the decision tree, or graph, the decision is yes. And then now we say, why did you conclude that Susan is pregnant? And now we want to compute the sufficient reasons. Now, interestingly enough, one of them is this. That is this characteristic. That alone guarantees that decision. If the scanning is positive, this classifier will decide that the patient is pregnant regardless of the values of these 2. It's interesting because if you look at the decision tree and how it's classified, this actually doesn't even appear on the decision path, right? So even a simple example like this can be surprising. Now, there is actually 2 sufficient reasons in this case, and this is the second one, which is the one that was captured. By the way, check it. This may look surprising, but if this scanning is positive, there are 4 cases, depending on what the value of blood and urine, and try all 4 cases in this decision tree, a graph, and you'll find that in all of them, you'll land at the yes decision as well. Okay, let's look at a more substantial example. This was a neural network classifier in the form of a convolutional neural network, or a CNN, that we learned to classify black and white images. They're 16 by 16 pixels. The goal was to distinguish between 0 and 1 digits. And in this case, the classifier did indeed conclude that this is a 0. And sufficient reason in this case, you have to realize that there are 256 features, right? The number of pixels in the image. And each one of them could be on and off. So when I tell you, give me a sufficient reason, I'm asking for a minimal subset of these pixels, 256, that guarantees that this classifier will say that this is a 0. And in this particular case, one of the sufficient reasons was this, that these 3 pixels are white. And as long as these 3 pixels is white, this classifier, these 3 pixels appear here. The classifier will conclude that this is a 0 regardless of what the other pixels are. So it will guaranteed, it will classify this image as 1 because in this image, these 3 pixels are actually white. All right. And that gives you a sense of this notion. And here's another example where this was classified as a 1, and this was one of the sufficient reasons. As long as these pixels are black and these 2 are white, this will always be classified as 1, including this image, which is compatible with this. Since then, the introduction of this notion of a PI explanation or sufficient reason, as we'll see later, they're also known as abductive explanations. People call them that later. There have been many, many papers on this notion, particularly on algorithms and complexity of computing sufficient reasons, counting them for various situations, complexity of computing even a single one of them, and so on. Now, what I want to do next is under the excuse of telling you why did we call these PI explanations, I want to explain to you what's the reason for that name. But my goal is I need the technicalities behind this slide, all right? Because this slide tells you how we computed them initially, which was the reason for the name. And we computed them based on the notion of prime implicants, which are what they've been around for at least 50 years in computer science, and their dual notion prime implicates. So if you have a Boolean function like this, expressed using this expression, and remember our notation, this means A is true, this means A is false. And a prime implicant is a minimal way for triggering the function. So I have 3 variables. Is there a minimal way to set these variables to trigger the function to generate a 1? And in this case, there are 3 prime implicants. So this is the first one. It says, if you set A to true and B to true, this function will trigger. It doesn't matter what C is. And you cannot make this any shorter, right? If you drop this or drop that, that's no longer the case. And here's another prime implicant. Here's another prime implicant. If you look at the complement of the function, it's this one. These are its prime implicants. So if A is false and C is true, then this function will generate a 0. F will generate a 0. And there are 2 more in this particular case. So how did we use this notion to define sufficient reasons? It's very simple. First, by the way, you can think of this now as a binary classifier. It has positive instances and negative instances. And this formula is the positive class formula. It's the formula that characterizes the positive instances, and this is the formula that characterizes the negative instances. Now, you give me an instance like this, and it turns out to be a positive instance. F will be 1 at this particular variable instantiation. So the decision is 1. And you say, why did you make that decision? We're trying to explain this decision. So the sufficient reason is very simple. It is the prime implicants that are compatible with the instance. And in this case, 2 of them are compatible with this instance, and these are the sufficient reasons. And that's why we call these PI explanations when we introduce them. If you had a negative instance, you have to work with these prime implicants. In this case, which ones are compatible with this negative instance? There's only one of them, so this is the sufficient reason. There's only one sufficient reason in this case. Now, there is the dual notion of prime implicates, which will play a role later also. Here, instead of a conjunction that triggers the function, we're looking for a disjunction that's implied by the function, and we want it to be a minimal or shortest, a minimal disjunction that is implied by the formula. Again, we'll get to this later. But one of the main issues with prime implicants, and this is what motivated us to discover something that I'll discuss next, which was meant to address this issue, but ended up being significantly more profound and led to new contributions to symbolic logic, as you will see, is that it's known that the number of prime implicants and implicates could be exponential. And in this case, you may have to compute an exponential number of things to filter them based on which ones are compatible with the instance to then get to your sufficient reasons. And our motivation in what I'm going to be talking about was to try to do something about that. And the reason is, as there are questions that rely on examining sufficient reasons, and we want to again to find ways to do that without having to go through this enumeration process that is implied by this method. Now, so we discovered something for that purpose. Now, what I'm going to introduce it's going to be under the notion of a complete reason. And it was introduced in this paper a couple of years after the notion of a sufficient reason or PI explanation was introduced. The way I'm going to explain it here is not how it was introduced in the original paper. In fact, that's going to happen in a lot of places in this tutorial. I'm doing a reconstruction of what happened over the last 5 years based on our current understanding. Some of the definitions I'm giving here appear as theorems in the original papers and vice versa. Some of the theorems are actually definitions. So again, the description I'm going to give you now for the complete reason is not how it appeared in the original paper. So we're going to look at it now as the notion of a complete reason as an abstraction of the instance that led to the decision. So you give me an instance and you tell me the classifier made this particular decision, and I want to know why. And I want to give you a description, an abstract description of this instance that is the culprit behind that decision. And then we'll see that if we get our hand on that condition or that abstraction, we can use it to compute sufficient reasons more efficiently and actually do a lot more, as we found out later. So what is this guy? I'm going to put it in words, and then I'm going to give you the formal definition. Okay, we have to focus here because this is fundamental in many ways because of the implications of this notion, because to formalize it, we ended up introducing notions that are profound from a symbolic logic point of view. And again, we'll find that there is a next version of it towards the end of the tutorial. Okay, so what are we doing here? It's very simple. Maybe you want to ignore what I wrote here and just focus on the following. An instance is a set of characteristics. So the complete reason is the following. I allow you to come up with a condition on the instance that tells us why it was classified the way it was classified. But I'm going to put some constraints on you. First of them, you can only use, in constructing this condition, you can only use ands and ors, right? These are the only logical connectives you can use. Second, the atoms or the ingredients, the things that you start combining using ands and ors must be characteristics in the instance. So and remember, a characteristic is a state of a variable, is a simple literal. So you're only allowed to use simple literals to start with, and these simple literals have to appear in the instance. And then you can combine them as you wish using and or, with the requirement, first, that condition is sufficient to trigger the condition, meaning the decision, meaning any instance that satisfies that condition will be classified similarly. And second, I want the weakest such condition. All right. So formally, the complete reason for the decision on an instance I is the weakest NNF. Remember what an NNF is a formula that's constructed using ands and ors, no negations. Is the weakest NNF whose literals are in I, and therefore these must be simple literals. They must be characteristic. So, and we have the following condition. What is this? This condition is satisfied by the instance, so it acts as a description of the instance. This condition implies the class formula, so it triggers the decision. Again, this part here tells you that it is a condition on the instance, right? It describes the instance. And this part tells you that it triggers the decision. And I want the weakest one. That's the abstraction part. So given the restriction I put on syntax, this complete reason is both necessary and sufficient for the decision. All right. And I'll show you next a visualization of it. But let me emphasize again, and that should be obvious from the definition, that the complete reason is a simple formula. That is, it is an NF formula, negation number form, but all of the literals are simple. They're states. All right. This is important because later we're going to talk about a recent development that happened over the last couple of months, where we get to relax this condition and we find that we have a way more generalized theory of explainability compared to what happened over the last 5 years or so. But let's visualize this notion of a complete reason using a concrete example. And this is a classifier with 4 features. It's about admission based on SAT score, GPA, an essay, and an interview. And let's look at this applicant here. So it's an instance. It has values for each one of the 4 features. SAT is a binary variable. Either the score is less than this or greater than or equal. GPA is multi-valued. essay and interview are binary, pass, fail. So for this instance and this classifier and the implied class formulas, if you use the definition that we gave, you get the following complete reason. Now you're going to tell me, how did you compute that? I'll tell you later. And that was one of the places where you'll see a contribution to symbolic logic. There is a very nice operator that can be used to compute this notion of a complete reason. But the main point I want you to see here is it's an NNF circuit, actually. The leaves are all either simple literals, that is states of variables, variable settings. All of these simple literals appear in the instance. That's very important. That's part of the condition. And you have also these constants. The reason you have them here is because this was generated automatically. This can be simplified. And then you have ands and ors, all right? So trust me, this is the weakest such condition, all right? It does trigger the reject decision. Any instance that satisfies this expression or this condition will be rejected. And it's the weakest such thing that can be constructed using an NNF whose simple literals come from the instance. Okay, now, here's the first surprise, or the first benefit of having the notion of a complete reason. If you compute the prime implicants of this circuit, those are precisely the sufficient reasons. Now, remember the definition of a sufficient reason. We look at the class formula, compute its prime implicants, and then filter the ones that are compatible with the instance. In this case, there is no filtering. Any prime implicant of this expression is immediately a sufficient reason. No more filtering. So if you had an exponential number of prime implicants of the class formula and a polynomially sized or a polynomial number of sufficient reasons, you're not going to have a problem here because you don't have to go through exponential to get the polynomial. Very good. So that's one of the benefits. In fact, that's the reason we introduced it initially. That's what we were after. But as you see now, this ends up being more influential than this. Later, I'll show you how we compute this, and that's relatively recent advance. This theory of formal explainable AI has been around for about 5 years in the form that I'm going to be discussing, and this is about maybe a year and a half, the method for computing this using a new logical operator. And because of that, we can now obtain for decision graphs, we can obtain these complete reasons in closed form. By doing just a sweep through the decision graph, we can generate this very efficiently linear time, actually closed form. That's described in this paper here. That basically shows how you can obtain these complete reasons in closed form for decision graphs. But let's take a concrete example, and then I'll tell you about another major use of the notion of a complete reason, which we were not anticipating when we introduced it. So this is the instance we looked at. This is the value of this feature and so on. And we saw that this is an applicant that was rejected, and we saw that this is the complete reason. So if we compute the prime implicants, we get 2 of them, this and that. Now remember, what is a prime implicant? It's a term, it's a conjunction. And in this case, it's guaranteed that these prime implicants will be simple terms. That is, every literal is simple, is a variable setting. And again, all of these variable settings must appear in the instance. So the first one tells us effectively that the essay didn't matter. So for this applicant, even if they pass the essay, they will still be rejected, okay? So the second one is a bit more interesting. It says, listen, As long as the applicant fails their essay and interview, they will be rejected. It doesn't matter what their GPA and what their SAT score are. So very useful notions. Again, these are, you can think of them as we discussed initially, a minimal subset of these characteristics that guarantees the decision. Now, there's also the notion of a length minimal sufficient reasons that was discussed. We talk about that in this paper as well. There are actually other references you'll see in the paper that goes with this tutorial. This has been also studied, and various results on counting and complexity were shown in the literature. A sufficient reason is subset minimal, and people want length minimal, which is the goal is to try to even generate a smaller number of them. So in this case, this would be length minimal, all right, because it has 2 versus 3. Okay. Now, I'll tell you about something that came later, which is, and maybe this is a question that you'll be asking. So, okay, I compute the prime implicants of this guy, and they turn out to be the sufficient reasons. What if I compute the prime implicates? Typically, a formula, you talk about its prime implicants and prime implicates. What happens if I compute the prime implicates of this guy? And we refer to these as necessary reasons for a very good reason in this paper. But and we showed that actually they correspond to what is known in the literature as contrastive explanations. I'll tell you about contrastive explanations in a second, but those are I'll tell you how you can modify the instance in a minimal way to change the decision. All right, and they do correspond to the prime implicates, of the complete reason, and we call them necessary reason, and you'll see why. They correspond to clauses. So let's take a concrete example to illustrate this notion. So we'll use the same example, the same instance that was rejected. And here's the complete reason. But in this case, let's compute the prime implicates. Now, implicants are terms that imply the formula. Implicates are clauses that are implied by the formula, and they're minimal. So in this case, you get 3 of them. So this and this and that. So this is, in this case, a trivial, like a unit clause. There's only one variable setting. This says this or that, this or that clauses, right? Again, the literals are all simple and they appear in the instance. That's all guaranteed. Now, and this is why we call them necessary reasons, because they're necessary for the decision. If you violate any of them, the decision is no longer guaranteed. Now, how can I violate the first one? There's only one way, to flip this to a pass, all right? And in this case, if you take this instance and indeed change interview to pass, this applicant will be accepted, guaranteed. Now, let's try to violate the second necessary reason. And how do you violate this condition? It says this or that. You violate it by negating this, negating that. And again, these are both binary variables. The only way to do this is this way, is to set the SAT score to this and the essay to pass. And again, in this case, if you change this instance this way by changing these 2 features this way, guaranteed this applicant will be accepted. Now, here's something interesting for the last one. The last one, this variable is binary, but this variable is ternary, has 3 values. To violate it, I have to negate this and negate that. So there are 2 ways to do it. To negate this, I have to set this to pass. But in this case, I can set this to either low or high. So there are 2 ways to actually violate this necessary reason. And the only guarantee here that you get is that at least one of them will flip the decision. There's no guarantee that all of them will. And in this case, actually, one of them does, the other does not. And this is going to be important because in the latter part of this tutorial, we'll see these recent developments that happened over the last few months that introduce a more powerful notion than the complete reason, and lead to a new type of sufficient reasons and a new type of necessary reasons that are more powerful than these. And you'll see that the secret for doing that will rely on working with discrete logic as opposed to Boolean logic. And again, you'll see the details later. But again, people have been interested also in length minimal necessary reasons. This paper discusses them, including algorithms for computing them based on this theory that I discussed here. But there are other works in the literature that also discuss these notions. So this is the picture that we have now. It's very elegant, very simple. The idea is and now we have a full theory, right? You take your classifier, you compile it into class formulas. Once you have the class formulas, you can compute complete reasons from their prime implicants and implicates. You can get sufficient and necessary reasons, and you get to do all of these wonderful things. Now, I'm going to tell you how to compute this guy and say a few words on also how to compute the prime implicants and prime implicants. This is more interesting because this is very new. This is a more traditional subject. There's still innovations there and new results, but the key thing is how to get this. And there we'll see some profound contributions to symbolic logic, because we will introduce new operators for abstraction. As you will see, because the notion of a complete reason is an abstraction. But let me just say a word on terminology, because that gets confusing in the literature. We did introduce PI explanations, as I said, in this paper, 2018. And then later we call them sufficient reasons. And I hope you understand why, because the notion of sufficient reason, necessary reason, complete reason makes sense. Later, people call these abductive explanations. You're going to find a lot of papers in the literature about abductive explanations. These are PI explanations as we introduce them, or what we now refer to them mostly as sufficient reasons. Necessary reasons, as I said, the original notion is the notion of a contrastive explanation, which is pretty old. The discussion we had is based on this formulation in this paper. These are also known as counterfactual explanations. And I have parentheses because, at least in this paper, the notion of a counterfactual explanation was a length minimal one as opposed to a subset minimal. But as we so later, we found out that if you compute the prime implicates of the complete reason, that corresponds to contrastive explanations. And you saw the justification for why that is a necessary reason, because if you violate it, you undermine the decision. And again, this is the paper that introduced the complete reason. That has not been renamed yet, but we will see. Okay, now we're going to get to the interesting discussion about how do we compute the complete reason. And we will end up introducing an abstraction operator for that purpose. But I need to review a couple of notions. One of them is because they will be used as ingredients in defining that abstraction operator. And by the way, the abstraction operator not only will give us an elegant way to formulate the notion of a complete reason, but also it will be the basis for doing computations, for computing it. The notion of conditioning a formula is fundamental in Boolean logic. And now we're going to look at the generalization to discrete logic. So delta is a discrete formula. And this is a simple literal, that is a state of a variable. I want to condition the discrete formula on the state of that variable. And the process is pretty simple. I will have to go and find every X literal in this formula, every literal for that variable. Let's call it L. And I have to replace it with either true or false. So after this conditioning process, the variable X will no longer appear in the formula. Every time it occurs as a literal, that literal will be replaced by either true or false, depending on whether this state appears in that literal or not. Right? So let's take a concrete example. This is a discrete formula. This says variable X is either 1 or 2, and so on. And I'm now going to condition it on a term. Now, here I define conditioning on a state, but the conditioning is commutative. So I condition on this, then on that, or the other way around, you get the same results. So it's meaningful to talk about conditioning on a term. And what will happen here is very simple. First, for this, there are two X literals, this one and that one. This guy does not appear in this, so this has to become false. This has to become true. And for Z, this state appears in this literal, so this is replaced by true, and therefore I get this result. So the final result is this. This is conditioning. It generalizes the notion of Boolean or conditioning a Boolean formula. Now I'm going to introduce this abstraction operator. All right. And I'm going to throw the formula at you. And we're not going to make sense of the formula yet. Okay, we're going to discuss its semantics, but the key thing for you to see it's well defined. All right, and this came of in work with Pierre Marquis. So let's say you have a variable X and it has these states, and here's the operator. The operator is we called it then a quantification or universal quantification operator. So I'm quantifying the state, this particular state of the variable from the formula. So this is the quantification operator for all. And this is defined as follows. Again, this looks like, where did you get this from? I mean, if you look at the original paper, you're going to see very nice reasoning for where this came from. But all you have to know here is, we know what this is. I'm conditioning the formula on the state. And this is obvious. I'm conditioning it on other states. So this is well defined. Now, the main thing is the following. First, this operator is commutative. What does that mean? That means it's meaningful to do the following. Suppose you have this formula, and every variable has 3 values, and it's meaningful to write this. What does this mean? This says quantify all these 3 states from delta. And I'm not specifying the order because the order doesn't matter. This means just in any order, apply this operator. Apply to this, apply to this, apply to that. Okay, so first, again, doesn't matter what the order is. Now, we're going to even do something nicer in terms of notation. We will, suppose we have a simple term like this, which is variable instantiation, right? So X took this particular state, Y took this particular state, these took this particular state. We will write this. Quantify this term from the formula, which means the following. Quantify every state in that term from the formula. And in this case, if you apply the definition, you're going to get this. What's going to happen is this is going to be a class formula, and this is going to be an instance. And as you'll see next, this is going to be our abstraction operator. So remember our friend, the complete reason, which we defined as the weakest NNF formula, or whose literals appear in the instance, are contained in the instance, or simple literals appear in the instance, and that satisfies this condition. Well, here you go. I can get you this guy this way, meaning you give me the class formula, and I quantify the instance out of it using the definition that I just gave you. And that result is an abstraction of the instance. It's the weakest condition on the instance that triggers the formula. The only condition I have on this, the only restrictions I have on this condition is that its ingredients must come from the instance itself. So you can only use states that appeared in the instance, and then you can only combine them using and or. This is this part here. All right. So the complete reason, once more, is both sufficient and necessary for the decision under the restriction that we mentioned, that you can only formulate it using states that appeared in the instance. Okay, that's pretty important, and you can get it beautifully using this operator. Now, that's not the end of the good news. It turns out that this operator is very well behaved, and it distributes. It distributes over conjunctions, and it distributes over disjunctions when the disjuncts do not share variables. Remember the earlier discussion on tractable circuits? And I told you later I will tell you a property or a type of a tractable circuit that facilitates computations related to explainability. What I'm mostly interested in here is how do I facilitate the computation of the complete reason? Because once I grabbed it, I can compute its prime implicants and prime implicates, and I get my sufficient and necessary reasons. Well, that's the class that we need, or the composable NNF circuits. So NNF circuits, just circuits that at the bottom, you have literals or constants, and then you can only have ands and ors. And now I'm just requiring one condition. Anytime you have an or in this circuit, I want the disjuncts not to share variables. That's or decomposable. If your class formula is represented as an or decomposable NNF circuit, then you can compute complete reasons for any instance in linear time. Interestingly enough, if you look at the theory of tractable circuits that has been under development for over 20 years with dozens of papers written, the or decomposable property was not there. We talk typically about and decomposability. If people who know decomposable negation normal form, DNNFs, those are and decomposable, not or decomposable. So that turns out to be a very important property in this particular context. Okay, so here's the picture. And this summarizes this theory that I discussed. So you have a classifier with some classes, and somehow you compile the corresponding class formulas. You get an instance, the classifier makes a decision on it, puts it in this class, and then what you need to do is pick the corresponding class formula and compute the complete reason using this operator. And once you have it, its prime implicants will tell you what minimal subsets of it guarantee the decision, and its prime implicates tell you what are minimal ways in which I can change the decision. What are minimal ways to change the instance so that I undermine the decision? Now, I have to say a couple of things. I will tell you something about how do you compute these guys, but I want to just emphasize something important. There's a lot of work in the literature that is computing sufficient reasons or abductive explanations or PI explanations, whatever name people prefer to call them. Everybody has their preferred name. Or necessary reasons, contrastive explanations, counterfactual explanations. And a lot of these works do not do this, do not go through the notion of a complete reason. In fact, quite a bit of these works predates the notion of a complete reason. So there are a lot of works that bypass this notion and directly try to go and compute these because both of them had definitions that are independent of the complete reason. And in the paper that goes with this tutorial, you'll find some representative or a sample of some of the good references that actually do that. Now, in this case, what are we going to do? You're going to say, okay, we talked about how to do this. The secret is if you have an or decomposable circuit, then you're good. So maybe that's what you should do. Okay, you try to get your formulas as or decomposable, and later we're going to see that at least for one class of classifiers, how this can be done nicely and efficiently. But what about these guys? Now, yes, there is. This is a more traditional problem, computing prime implicants and implicants, but it is traditional and has been studied extensively, but for certain classes of formulas, typically CNF, DNF, not as much when you talk about circuits. As you'll see later also, we will need to do these for discrete circuits. That means the literals are not simple. So there's, for that, almost none as far as we know. But the good news here is the thing that is implied by what I said, but let me mention it clearly. The complete reason circuits that are computed by this operator are monotone. Now, in Boolean logic, you typically talk about a CNF being monotone, which means that every variable appears either positively or negatively. You cannot have X and not X appear in the CNF. So it's either all X or all not X. And that is a property that has computational implications. In discrete logic, the notion of monotonicity can be defined like this, that all literals of a particular variable are simple and equal. So first, you cannot have general literals. They have to be states, and they have to be equal. And in this case, that is indeed satisfied by complete reasons. In fact, trivially, by the way we defined it in this tutorial. So we're not talking about the computation of sufficient and necessary reason, the prime implicants and implicates of arbitrary NNF circuits, but of monotone ones, and that gets facilitated. These papers discuss this issue in particular. This one in particular has a number of algorithms that do take advantage of this monotonicity property. Okay. Now I'm gonna turn to an exciting and new development in explainable AI, or in formal explainable AI. The observation I'm going to start with is not new. In fact, the first time this was observed is in this paper we had. It was in a workshop and on the archive. So I'm going to start with that observation. And there has been interests here and there of people trying to do something about it, but only recently, and I'll show you the reference. 2 months, 3 months ago, we had came up with a comprehensive solution to the insight that I'm going to mention now. So what's going on here? Okay, let me tell you. But again, before I start, the short story is, if you take the theory that I discussed, which originally was developed for binary variables, particularly the sufficient reasons, and you apply it to discrete variables as is, you miss. You end up being suboptimal. The explanations you get are not informative enough. They can be improved significantly. All right. Again, this was observed initially in this paper. Let's take a look at the key insight. The key insight is, let's look at this particular classifier. All right. It's a decision tree. We have diabetes and weight, which has 3 values. Blood type has 4 values. And let's take this particular instance or patient Rob. Right, so they've got diabetes, underweight, and blood type of A, and they get classified as yes. If you apply the theory that I told you, and you say, what are the sufficient reasons in this case, you're going to find there's only one sufficient reason, which is this guy. And remember, what is a sufficient reason? It's a minimal subset of these 3 that guarantees the decision. That's the only one, which effectively means this was irrelevant. I needed the reason why this was classified is their blood type is A and diabetes Y. Well, turns out, no, you can do much better than this. And you can come up with weaker sufficient reasons. And I'm going to give you 2 of them here. The first one is this. This says, listen, the reason why Rob was classified as yes is because he has diabetes and because his blood type is not one of these. Okay, it's not because his blood type is A. A is irrelevant, actually. What's relevant is it's not one of these. If you want to write this formally, here's the sufficient reason, or a weaker sufficient reason. Yeah, he has diabetes and his blood type is in one of these 2. Now, this can never be generated by the current theory, because the current theory insists that the explanations are sufficient reasons are terms or are characteristics that appear in the instance. That's the only language you can use, all right? So this is not part of the game, all right? And here's another interesting, weaker sufficient reason. Rob has diabetes. His weight is not norm. Okay, here it says weight under, but this says, no, it's not about being under. It's about being not normal. So it could have been under or over. And his blood type is not O. Yes, it's A, but that's not the issue. The issue is that it's not O. And in fact, if you can check, by the way, I should have told you about this too. You can check diabetes and A, of course. The diabetes, yes, and blood type, you will do it. And you can check that this will trigger the decision. Diabetes, the weight is in one of these, right? Satisfied here. And blood type is in one of these, satisfied by that. Again, this will not be generated by the current theory because of the insistence of the literals coming from the instance itself, all right? That you can only use simple literals when you phrase sufficient reasons or necessary reasons. As I said, this actually was observed in this paper, all right? And there was a solution that was suggested there based on actually the first version of discrete logic that we later refined. But there was no comprehensive theory. And in fact, what we're going to present will deviate from that a little bit. And it's going to be based on a new notion of abstraction, like the complete reason. And by the way, others have danced around this notion as well. But again, the paper I'm going to show is the first comprehensive solution to this problem. Here's the paper, which just appeared a couple of months ago. It is based on this new notion of the general reason. Okay, the point is, if you see what I just told you, and you say, okay, so what happened? This whole theory that you told me up to presenting this key insight, what was missed? Why didn't we arrive at these? And here's the secret. Remember our definition of complete reason, all right? We will take it and change one single part of it, which is this. This is the notion of a general reason. This definition is exactly like the complete reason with one exception. In the definition of a complete reason, we said it is the weakest NNF whose literals are contained in I, and that satisfy this condition. Now I'm going to say, no. They don't have to be contained in I. They just have to be implied by I. Now, contained in I immediately necessitates them being simple literals, because the only literals that can appear in an instance are simple literals, states. Now I'm telling you, no. When you are coming up with this condition that represents an abstraction of the instance, and it is the weakest one that is a description of the instance and that triggers the decision, I'm not going to constrain you to only use literals that appear in the instance, but I'm going to constrain you to use literals that are implied by the instance. All right? And everything else is the same. You can only combine them using ands and ors. That's why you have an NNF. And I want whatever you come up with to be satisfied by the instance, so it qualifies as a description of the instance. I want it to imply the class formula. That is, it triggers the decision, and I want it to be the weakest one. So again, this guy is both necessary and sufficient for the decision under the current syntactic restrictions. And the more pleasant news, and I will see, we'll use this to define a generalized notion of a sufficient reason and a generalized notion of a necessary reason. But first, how do we compute it? We also have an abstraction operator, which tends to be simpler than the previous one. So again, here's a variable x. It has these states. And now I'm defining this operator. Okay. For lack of imagination, we ended up using for all with a bar on top of it. We'll probably change this notation. So we're quantifying the state out of that, and this is the definition. It's simpler than the previous definition. Just take the formula, condition it on the state, and then take that, conjoin it with the formula again. All right. And the theorem is, if you, and again, this is commutative, just like the previous abstraction operator. So if you want to quantify a bunch of states, you can do them in any order, and therefore it's meaningful to write this. So if you take the instance and quantify it out of its class formula using this, you get the general reason. you get a formula that corresponds to this guy. Remarkable. Again, this is recent. And now I'll tell you about what you can do with it, but I have to emphasize that this operator and the other one end up corresponding to each other if the variable x is binary, has only two states. So this notion of a general reason is only useful beyond the complete reason when you have discrete variables. If everything is binary, these two theories collapse to each other, all right? And this guy also distributes like the previous abstraction operator. So again, if your class formulas are or decomposable NNF circuits, you're in heaven. You can compute general reasons for any instance in linear time and the size of the circuit representing the class formula. Okay, let's take some concrete examples to make some more important, additional important points. This is the same example we looked at, but and this is Rob, right? So the complete reason for this decision on Rob is this, and the general reason is this. And as you can imagine, here are all simple literals. Now I do not necessarily have simple literals. Now you're gonna see later that the complete reason always implies the general reason. So general reason is a weaker condition. So we'll show you a nice general relation later. But I want to tell you, the paper, this paper actually has a whole section dedicated to this subject. This business of what you will miss if you don't do what we just started doing now is most significant when you talk about things like numeric decision trees or random forests where variables are discretized. If you apply the previous theory that computes these simple explanations, you miss a lot. And here's a concrete example. We looked at this before, right? So we have an instance, age 42, let's say, and BMI 28, and it gets discretized into A3 and B3 based on this mapping of intervals to discrete values. So effectively, this classifier is looking at this as belonging to the equivalent class that says age is greater than or equal to 40 and BMI between these two. So basically, any other instance that satisfies this condition will be treated similarly. Now, the decision is yes. The complete reason in this case is just this, the instance itself. So the complete reason did not do any abstraction. The general reason is this, which when decoded looks like this. So, okay, let's see what happened here. When you use the existing theory that computes these simple explanations and you tell it, why did you classify this instance as yes, it will tell you because the age is 42 and the BMI is 28. Or another way, because the age was greater than 40 and BMI was in between these. This guy saying, oh, wait a minute. No, okay, let me tell you. First, you can look at it in two different ways, why I did it. One of them is because the age is greater than or equal to 18 and BMI is greater than or equal to 27. Okay, that's satisfied by this. Another reason I can justify what I did is age here is greater than or equal to 40 and BMI is greater than or equal to 25. This is an abstraction of this instance. This is not an abstraction. And I hope you can see why the current theory would never be able to do better than this, because it cannot use anything other than this and that as literals and then combine them using ands and ors. But in this case, no, I can use literals that are more general than these two. So this new theory is significant in this class of applications or for these type of classifiers, and I hope this point was made clear. Okay. the original theory defined sufficient reasons and necessary reasons as the prime implicants and implicates of complete reasons, which as we saw, gets computed in this particular way. The new theory does it similarly, with an exception. So there is now the notion of a general sufficient reason, GSR, which is the variable minimum prime implicants of the general reason. Okay, so and the general necessary reasons are the variable minimum prime implicates. Okay, so let's ignore variable minimal for now. The only difference is instead of complete reason, we use general reasons. And this, what is variable minimum? So let's say you have a prime implicant. It mentions variables x, y, z. And another prime implicant mentions variable x and y. Then this guy is not minimal, not variable minimal, because it mentions a superset of the variables that are mentioned in that. So I'm going to exclude it. Now, you're going to tell me, why did you guys do that? We provide a number of justifications. Basically, we argue that these guys have very nice properties. We do not exclude the usefulness of prime implicants and implicants that are not variable minimal, but we proved some very strong properties for these particular subset, and you'll see in just a little bit with the concrete examples what guarantees come with these particular guys. So, for example, these already include all of the simple sufficient reasons and necessary reasons. So there's strict generalizations of them, and you got a hint of what you gain from this through the motivating example. And I'm going to show you an example that shows you what this gives you in terms of value compared to the standard necessary reasons. All right, so we're going to do this next. And again, the paper on the archive that just came up a couple of months ago, 2-3 months ago, have an extensive discussion on this variable minimality condition. And just again, to make sure, these standard notions that have dozens of papers dedicated to them, the explanations in this case are simple terms, okay? Conjunction of states. In this case, simple clauses, disjunction of states. Now we're working with general terms and general clauses. This is the example. I'm going to revisit it again. Just stressed again the point of general sufficient reasons, which we already got a glimpse of. But then I'll tell you what does the notion of a general necessary reason give you in comparison to the traditional or simple necessary reason. Okay, so same example we looked at before, but let's take at a new patient, Lara, has diabetes, she's overweight and blood type A. And she's classified as yes, and okay, you can get the class formula. We needed this for the computations. We can ignore it. Let's look at sufficient reasons. So if you're using the old theory, you compute the complete reason using this operator by quantifying this from the class formula that I just showed you, and you get this complete reason. Again, remember, everything is simple literal here. If you compute its prime implicants, which happen to be the sufficient reasons, you get these two. Okay, now let's see what happens with the new theory. With the new theory, you compute the general reason, and you quantify from the class formula using this operator. So you compute a new abstraction, and you get this. Again, you can see now we have non-simple literals. If you compute the prime implicants of this, you get 3 of them. Not all are variable minimal. The last one is not variable minimal. These 2 are variable minimal. So these are our now general sufficient reasons. This we have seen before, but you can see that this is providing more value compared to the previous one. Just like in the case of Rob, it was more interesting. But this example is actually meant for what's coming next, which is necessary reasons. Okay, let's look at necessary reasons. So again, if you're doing it the old way, you would compute the complete reason, and then you compute the prime implicates, which happen to be the necessary reasons or counterfactual explanations or contrastive explanations, and there's 2 of them. Now, remember, what did we say about these? What is a necessary reason? Is something which is a property of the instance. It's a disjunctive property of the instance. And if you violate it, you undermine the decision. Okay, so let's look at the first guy. there is only one way to violate this guy, by saying diabetes is no. And in this case, if indeed you do that, the decision will flip. The second guy, there are 6 ways to violate it. It says weight is over or blood type is A. So I have to negate this, negate that. So actually there's 6 different ways in which I can change the instance to violate. Half of them, the ones in black, do indeed flip the decision. The ones in red do not. So all I'm guaranteeing you is there is a way to undermine the decision by violating this guy. But if there are multiple violations, I'm not telling you which one will do that, but I'm telling you at least one of them will. Okay, now we get a stronger guarantee with the general necessary reasons. Okay, so now we compute the general reason, which we've seen. If you compute its prime implicates, you get 3 of them. And all of them are variable minimal. So all of them are GNRs, or general necessary reasons. Now, the guarantee you get here is not only will violating the necessary reason undermine the decision, but every way of violating the necessary reason or a necessary reason is guaranteed to undermine the decision. So in the first guy, that's trivial. There's only one way to violate it, by setting diabetes to no, and that will undermine the decision. The second guy, there are 2 ways to violate it, by setting blood type to O and this guy to either under or no. Check, you will find that both of them will undermine the decision or will flip it to no. And in the third case, this necessary reason, again, there are 2 ways to violate it, and both of them are guaranteed to flip the decision. So that's the power of these compared to the simple necessary reasons, is this one, every violation guarantees that you will indeed flip the decision. Okay, now here's the more general picture, and which is parallel to the previous one, except that we are computing a new type of abstraction of the instance, the general reason, based on this operator. And then I compute variable minimal implicants or variable minimal implicates. Again, it's a comprehensive formulation in this paper. And I just want to say now something also. I already told you how to get that by seeking or decomposable circuits, NNF circuits for the class formulas. You'll be able, if you have that, you get this abstraction in linear time. Now, how do I compute this? Now, earlier I made remarks that when talking about computing prime implicants and implicates, CNFs and DNFs receive the most attention. Circuits, less attention. Now we're talking about discrete circuits, not Boolean circuits. The ones that are at the bottom, you don't have simple literals, but you have more general literals, basically almost non-existent. And remember also what I told you about computing prime implicants and implicates of NNF circuits that correspond to complete reasons. I told you, luckily, those circuits are monotone, and that gets exploited when using when doing these computations. So you're not doing implicants and implicants or prime implicants and implicants of arbitrary NNF circuits, but monotone ones. Well, it turns out monotonicity is an actual degenerate case of a property called fixation that we also introduced in this paper. I'm going to show you next. And the general region actually does satisfy that fixation property. And that fixation property does play a similar role in facilitating computation of prime implicants and implicates. So this is a property. So I told you at the beginning of the tutorial that this theory of explainability is making new profound contributions to symbolic logic. These abstraction operators that I showed you that are used to compute complete and general reasons, very interesting, all right? And now I'll tell you about this property called fixation, which generalizes monotonicity. So what is fixation? An NNF is locally fixated on an instance That means its literals are consistent with the instance. It's a very simple definition. Let's look here. Here's an instance, and this NNF is locally fixated on the instance, because if you check every literal here, you'll find that it's consistent with the instance. Basically, this is compatible with this. This is compatible with this. This is compatible with that. Now, this is not locally fixated on the instance. Why? Because this guy is not compatible with that, right? So that's basically what locally fixated is. And if you recall the definition, the way we define the general reason, it's obvious that it's locally fixated on the instance. I'm going to show you next. I gave you a definition of monotonicity earlier, which was meant to convince you how it resembles the classical one known for Boolean formulas. Now I'm going to give you an equivalent definition of monotonicity that shows you how monotonicity is a special case of fixation. All right, the two definitions are equivalent. So we'll say the NNF formula is monotone if it is simple and fixated on some instance. So it is fixation with simplicity. And here are three examples. This shows that this is monotone. It is simple and it's fixated on this particular instance. This is not monotone because it's not simple. We've got this guy. And this is not monotone because these guys cannot be consistent at the same time with any instance and so on. So one quick benefit of fixation. You know, in Boolean logic, one way to compute prime implicates of a CNF is to close the CNF under resolution. And every step of resolution, you can throw out subsumed clauses, and you keep repeating this until you can't do it anymore. And then you get the prime implicate representation of the CNF. We defined a resolution rule for discrete logic. You'll see it in the paper. And then we use it to show the same thing. But if the CNF is fixated, then what happens is, and your goal is not only to compute a prime implicates, but your goal is to compute var min, variable minimal prime implicates. So if the CNF is also fixated, then after every step of resolution, you can throw out any implicates that you have that are not var min, that's sound and complete. So that's an example of what fixation allows you to do, all right? And I have two more quick subjects I want to mention, and then I go to the last part, which will give you some hints on how to compile class formulas. This is interesting. I'll tell you why. So targeting a new decision, something that is known in the literature as targeted contrastive explanations. Okay, here's the thing. Maybe, and some of you may have already asked that question. The notion of a necessary reason or contrastive explanation or counterfactual explanation tells you how to minimally modify the instance so you undermine the decision. Now, what does undermine the decision? It means the decision will no longer hold. Now, if you have two decisions only and you undermine one, that means you're going to the other. But what if you have three decisions? Undermining is not as useful. So let's look at a concrete example. So classifier, we have a classifier that decides whether an applicant will get a large loan, a small loan, or decline. So three classes, three class formulas. Now, I get an applicant who gets approved for a small loan. So the classifier is putting them in class 2, and that means that this instance, the applicant, implies that class formula. Now, if I compute necessary reasons and I violate one of them, then I'm guaranteed that some violation will kick this applicant from this class. But it does not tell me what's going to happen. Are they going to be given a larger loan or will be declined? There's a big difference between the two, all right? So the standard definitions do not really help with that. But suppose that's what I want to do. Suppose that I actually want to minimally change the application to approve a larger loan. Yes, I want to undermine the decision, but I want to target a particular new decision, which is a larger loan. One way to do this is nicely and simply is to merge these two classes. That is 2 and 3. Why are we merging? You merge everything except the guy you're targeting. So, and I just combined the two class formulas. So now I can think of having a binary classifier, a classifier where the instance is either approved for a large loan or the complement, decline or small loan. And in this case now, my applicant belongs to this new class, all right? And now if I go ahead and undermine this decision, then I'm guaranteed that the new decision will be the large loan. And you can do this by simply computing the general reason for this class formula instead of that class formula, right? Because the applicant is in this class now. I want to kick it out of this class. I'm guaranteed that it will land in class 1. And after that, you compute GNRs and so on. Now, targeted contrastive explanations were introduced and discussed computationally, but this particular technique, nice and simple, and because it's based on the notion of complete and general reasons, was actually discussed in this particular paper. Couple of words on the semantics of these abstraction operators, all right? And then we go to the last part about how do we compile class formulas. Now, remember, what is a classifier? Classifier is a partition of the instances, right? So here's a visualization of a classifier. And each class is, as we said, for us, we're represented by a formula that gives away the classifier. Now, what does this mean? You have an instance in one class like this one here. And what does this mean? Right? I'm computing an abstraction of the instance. That is the complete reason. What is that? Okay. Now, that's just another formula. So it characterizes another set of instances. So what are these instances? These are a subset of the class. So I is inside this circle. And what this guy is doing is pulling some members of the class that are similar to I in some way. And now I'm going to give you a word description of what are those instances that are selected by this abstraction operator, right? So let me read it. These are the instances in the class that remain in the class if any of their characteristics that are inconsistent with I are changed. So that means, let's say this is I and this is I prime, and they disagree on some features. They disagree on some features. Let's call them X, Y, Z. Then the fact that this was selected, that means for this guy, if I change X, Y, Z in any fashion, the result will remain in the class. So X, Y, Z are don't cares for this guy. That's why it got selected, okay? That's what this guy is doing. Now, what is this guy doing? Is selecting also a subset of the class, but a larger one. It's like a superset. And the description is almost the same. Remember the analogy. It said, here's I prime, and they disagree on X, Y, Z. Now, this guy said, I will choose it if and only if it remains in the class if I change X, Y, Z in any way. This guy says, no. I will not be as stringent. I will select it if it stays in the class, if I change X, Y, Z, so they match the values they have in I. So it's exactly the same definition with just the qualifier. So instances in class CI that remain in the class if any of the characteristics that they have and are inconsistent with I are changed to the values they have in instance I, right? So that's a weaker condition. So I end up choosing a larger subset. This slide is saying the same thing. Now we have this, which establishes these notions of complete reason and general reason as abstractions of the instance. So this is the instance, this is the class formula, this is an abstraction, this is an even further abstraction, and you have this wonderful, nice relationship between them. And remember once more, these two collapse to each other if every variable is binary, right? So they are distinct if you have some of the variables are discrete, have more than two values. And that's basically this comprehensive theory about explainability in the presence of discrete variables. By the way, this selection semantics was shown in this paper, discussed in detail, but for binary variables. And at that point, we only knew of complete reasons. This new paper discusses the generalized semantics that I just gave you, which applies to discrete variables beyond binary variables, and applies both to complete and general reasons. Now, you can do other things with complete reasons. Those were explored, and you can do similar things with general reasons. They have not been explored, but you can evaluate counterfactual queries, you can check decision bias and other things. So we're not going to talk about this here. But again, these notions, at least the first one was originally introduced to solve a particular technical problem, and they ended up being far-reaching, given that they are abstractions of instances. All right, so I'm going to spend maybe 10, 15 minutes to wrap it up and talk about compiling class formulas. Now, this is going to be quick. And what I wish to do is to just give you enough maybe to demystify the process of compilation, but that's a subject that requires a lot more time. Let's start again with this. As I mentioned, these guys are the simplest, and let's go ahead and just see why. Here's a decision tree. We saw that even though the variables are numeric, we can easily discretize them. In fact, when you look at this as a tree with discrete variables, it's already known how to get class formulas in the form of DNF. So if you want the class formula for class 1, you can trace every path to a 1, and every path will generate a term. You take the disjunction of the terms, so you can easily get a DNF. All right, so that's folklore. And it's efficient in this case, but if you have a decision graph, this actually may blow up. For decision graphs, you want to get circuits, and that can be done efficiently. You can easily get a circuit. So here's a decision graph, and we already talked about this earlier, how you can convert it into a circuit. But here you have to be careful, because this happens to be a decision graph where we have only 1 and 0. And then you got a Boolean circuit. And in this case, if you look at this is a binary classifier. So you have positive and negative instances. So you have the formula for the positive instance and negative instance. So what we got here is the formula for the positive instances. But more generally, what do you do if you have something like this? I have 3 classes. So I have 3 class formulas. So there's 3 circuits, a circuit for C1, a circuit for C2, and a circuit for C3. You can do the same procedure with one trick. If I want, let's say, the circuit for class C2, what I do is I replace this by 1 and these guys by zeros. So I turned it into a binary classifier. Is it in C2 or is it not? And then I apply this technique, and therefore I get the circuit for class 2. Okay, this all works, and you get class formulas in the form of circuits and enough circuits in linear time. Well, and people say, oh, this is also standard and folklore. Yes, but these circuits will end up being and decomposable. Remember, what we wanted, if we can, is to get or decomposable and enough circuits, because those are the ones that allow us to compute complete and general reasons in linear time. And in this paper, actually, there's a nice trick that shows how you can do that, actually, for decision graphs that satisfy either the test one property or what's we call the weak test one's property, which occurs in discretized decision trees. Numeric decision trees rarely satisfy the test one's property. A numeric variable is usually tested more than once. But that testing satisfies still a property called, we refer to it as the weak test one's property. And in both cases, we show how you can easily get circuits in the form of order composable NNFs. And that's why we were able to get closed form complete reasons and general reasons for decision graphs. So you can check this paper for that technique. It's pretty simple, actually. Okay, now, if you want to do random forests, if you know how to do trees, random forest, the easiest thing would be based on majority voting. So you just add a majority circuit. And so that's straightforward. As far as getting a circuit representation of the class formula or for each class in the random forest. Now, of course, getting an order decomposable version of that circuit is another story. A couple of words on compiling Bayesian network classifiers or getting class formulas of Bayesian network classifiers. Now, there's a couple of insights that underlies this. And the chronology is the first compilation method actually was 20 years ago, about 20 years ago, where we showed how to compile naive-based classifiers into decision graphs. And then later, tree Bayesian networks and then general Bayesian network structures. Now, in all of these, the result is a decision graph. But we already saw that if you have a decision graph, you can easily get circuit representations of the class formulas. Now, what's happening in these three works is pretty much the same insights, and I'm going to show them to you next quickly. But applying these insights becomes more difficult as you go down. So they're easiest to apply here, and they require more techniques to apply them here, and even more techniques to apply them here. And that's what happened in this progression of papers. So what are the insights? The first insights is this. If you look at this classifier that we looked at earlier, it had this distribution on the class variable, and this was the threshold. Now, in this case, believe it or not, if I drop this number to this, the classifier does not change. So any number between this and that, when you compile this, you get the exact same classifier. All of them will make the exact same decisions. And you can increase this to this, and the classifier will not change. Now, the numbers will be different, but as far as crossing this threshold or not, no difference. So you have this notion of an equivalence interval for the class distribution within which the classifier does not change. That's the main insight. The second insight is, if you know how to identify these equivalence intervals, then you can go and do the compilation of classifier. Here we're showing it for this guy by doing a depth-first search on the space of features. So we're doing the depth-first. We started with this guy, and we're saying, you know, let's set this positive, and then here I'm setting it negative. Now, here I did it differently. I set this to negative, this is positive. Now, look what happens here. Now, when you set this positive, negative, this classifier simplifies to this one. There's now only one feature, and the class prior changed, became a posterior, and it's this. Now, here I set them differently. So I got a different subclassifier. Same structure, of course, threshold doesn't change, but a different distribution on the class. So, but it happens in this case that this number and that number belong to the same equivalence interval. So this subclassifier and that subclassifier represent the same thing. They will make the same decisions. They are syntactically different as far as the numbers on the class variable, but they're equivalent as far as the decisions that they make. Now, if I know how to detect that, then when I compiled this guy into a decision graph, and I'm coming down here I will detect that I already solved that problem, then I don't do it again. And I just point to the compilation of the subclassifier. Okay, that's basically what's going on. Now, to do this, you have to know how to compute the equivalence intervals. You have to know how to do the caching in efficient ways and various other things. And the ability or the difficulty to do that increases as you move from naive Bayes to tree structure to arbitrary graph structures, and that's what's happening with these papers. So let me end with one more slide just on compiling neural networks. This is a subject that I hope we did more work on. We did just some preliminary work. There was follow-ups on it, and there's a lot more work actually in another community. I'll tell you about it. But so I'm going to tell you about the thing we did, which appeared in this paper, where we compiled neural networks under two restrictions. The inputs are binary. So you can use these for black and white images, like we did in some of the examples I showed you earlier. And we assume that the activation functions are step activation functions. So these are the two conditions. Now, they have serious implications. One of them is, look, let's look at this neuron. So all of the inputs are 0, 1. Now, this has a step activation function. What does that mean? That means the output is also 0, 1. So this neuron, which has 0, 1 inputs, 0, 1 output. So the neuron is just implementing a little Boolean function, right? Let's look at it. A, B, C, 3 inputs to the neuron. Here are the weights on the wires, and positive, positive, negative. And this is the threshold for the step activation function. So the neuron is basically doing this, checking this, and returning a 1 or 0, depending on whether this condition holds or not. Actually, this is equivalent to this Boolean condition. So whatever this is doing, it can be done by this Boolean expression. So if I know how to go from this to that, then what I can do is I can take every neuron and plug in, remove it, and put in the Boolean circuit that it's actually computing or representing. And if I do that, then that's it. I've got a Boolean circuit that corresponds to the neural network. Now, how do you do that? How do you take the neuron and come up with the corresponding Boolean circuit? Well, this is a linear classifier. What's happening here? If you look carefully into the mathematics behind compiling a naive Bayes classifier into a decision graph, which we just went over, the naive Bayes classifier is also a linear classifier. So actually, at some level, that same algorithm can be used to do this. All right? And that's what was done in this paper. In fact, this paper did something even better. Basically, it discussed an approximate version of this compilation algorithm that has pseudo-polynomial complexity if you assume that the weights have fixed precision. So, in fact, that's why we were able, and we use that approximation scheme, assuming fixed precision. It's not approximation. It is an exact algorithm, but its complexity significantly improved if you assume fixed precision. And we used it actually in this work, and that's why we're able to compile some substantial neural networks. Now, there is a lot more going in the area of encoding neural network symbolic. I actually don't know this work well, and I had to ask a friend to help me with some of the citations. So the tutorial paper that goes with this one, which appears on the archive and the proceedings of LEX, have a number of citations for other works. I don't know all of the details, but it depends on whether you're talking about a binary neural network where there's binarized versus quantized, and there are some sample influential works that are cited in that paper, so you can check them. But they're mostly meant for verification, as you will see. And at least for the 10 or 15 minutes that I just spent, those are inflated into 2 lectures in my graduate course on YouTube, if you want to hear more details about them. I think just one remark. This, complements, this line of work complements what we've been seeing in AI recently, where basically symbolic AI and CS methods are being used to reason about what was learned. Here, we focused on explanations, and people are doing also verification. And there's a big community like the VNN community, verification of neural networks, and they use complementary techniques and methods. Pretty exciting. All right, so I will conclude by pointing you to the our YouTube channel, where you will find more work related to what I discussed here. So thank you. And once more, thanks to the next conference for the invitation. Bye-bye.